My dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Center and School of Astrophysics and Astronomy, I'd like to welcome you all to our International Physics webinar. And today it's our 196th International Physics webinar. So as we know that we are staying in a Corona pandemic situation, it's very difficult for us to continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology has started this online program, including online international physics webinar. And we have successfully completed our 195th international physics webinar. And today it's our 196th international physics webinar. So today we'd like to welcome you all to a joint session between our department, Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, West Virginia University, USA. And we have with us here today Dr. Mikel Holcomb, Associate Professor, Department of Physics and Astronomy, West Virginia University. And I'd like to welcome our speaker. So good morning, madam, and good morning to here. So thanks for accepting our invitation. So before going to you, yeah, thank you. I'd like to introduce you with all of my students and the viewers. So dear student and viewers, I think you have already come to know that the title of this today's International Physics webinar title is the Understanding a New Type of Magnetism. And our speaker is Dr. Mikel Holcomb, Associate Professor, Department of Physics and Astronomy, West Virginia University. So if we see his educational and career background, you can see Dr. Mikel Holcomb, or Mickey Holcomb, is an associate professor of the Department of Physics and Astronomy at West Virginia University, and she got her PhD at UC Berkeley, and her advisor was Ramesh, topics multiferics, bachelor at Vanderbilt, advisor Torque, topics ultrafast optics, and did an internship at IBM spin relaxation. While she studied a variety of issues, her main project involved complex oxide magnetic thin film and magnetoelectric heterostructures. Some other current research areas include experimentally motivated machine learning efforts, ultrafast optical measurements, and synchrotron measurement. She enjoys collaboration, particularly with people interested in element-specific X-ray absorption, spectroscopy measurements, machine learning, or her high-quality complex oxide thin film. She has been funded by the National Science Foundation, the Department of Energy, the American Chemical Society, and NASA. So thanks again for giving us this opportunity to arrange such an important webinar with you. I think this will be very interesting for our students, and they might learn a lot of things. And this is a very good opportunity for our students to interact with you through online. So thanks again. You can start your session, madam. It's your time.
Yes, thank you so much for inviting me.
It's my pleasure.
I appreciate it. Let me just get my screen up here. All right, so as you heard in my bio, my group actually does a lot of things, and I'm going to tease about some of them so you get kind of a broader perspective. But also I'm going to be mainly focusing on one new discovery that we've come up recently, which is a new type of magnetism, which is very exciting when you discover something brand new. But to kind of motivate how we came across it and how we got into this, because it's always interesting when you hear, wow, you came up with something new. Everyone wants to know, well, how did you come across that? I'm going to kind of give the background story a little bit into, why we got into the field in the first place. I didn't start with this question right away. So before I get into telling you a bit about that, let me thank the appropriate people, because there are a lot of people to thank in this work. So all of my group is essential, but particularly for the work that I'm going to talk about today, one of the main contributors is Navid. He is the main person who discovered the main effect that I'm going to show you today. And he very graciously dealt with me while I told him for months that he was doing something wrong and kept telling him various ways that he needed to check it. which of course was valuable in the end because everybody had the same questions that I did, but he's steadfast and was able to prove it was a real effect. I also want to thank, in particular for this work, Robin. He grew a lot of the films that we're going to be talking about, very high quality films. So whenever you have something new, it's really nice to be able to say that's an intrinsic effect of your very high quality films instead of just, maybe just some side effect because you've got some gunk in the sample. So I want to thank them a lot. I also want to thank a wide variety of collaborators, and I'm not going to be able to show all of them, even though I'm going to show several on the screen here. In addition to our work at West Virginia University, and this is our department in the background, by the way, and you can tell it's a physics building, physics and astronomy, because we have a nice little observatory on the top of the building, and we also have a small radio telescope. We have some much bigger ones in our state, a couple hour drive away, which our astronomers take advantage of. But it's a nice building, newly renovated for us, so it's great. Well, besides the facilities in our building, and my lab is kind of on the other side of the building, but like up here, we go to a lot of national facilities around the country and sometimes around the world. One of the main ones that we go to is the Advanced Light Source, which is part of Lawrence Berkeley Labs, which one of the nicest things, other than scientifically, about going to this facility is you get such a beautiful view of San Francisco across the bay here. You can even see the Golden Gate Bridge from the experimental location, which is nice. But we also do some neutron measurements at NIST. And then we do some other synchrotron facility equipment near Chicago. And we've been to the magnet lab in Florida. So we've really been all over the place for this work. So it's been a lot of fun. And one of the most fun things besides just the locations is working with these experts because they've really seen everything. They use their fancy equipment from, everything from our, mildly boring looking samples that, just look like little chunks. But they've done things like look at dinosaur fossils, understanding the elements in those, or looking at arsenic and spider fangs. So they really have an interesting setup for some of the work they get to do. So a little bit jealous there. I also, so I'm going to talk a little bit about the growth in my group, but we're not primarily a growth group, although we do specialize in a few things. So we also collaborate with a few other growers. I haven't shown all of them for getting some of our films that we study in addition to what I talk about today. However, what I do talk about today will be films grown by our group. I also collaborate with a wide variety of theorists that specialize in different things, including computational work and machine learning, which is some work that we're starting to get more interested in. And you can't characterize everything, so we also collaborate with a large number of characterizers, people that specialize in ultrafast optics or special techniques and electron microscopy. So all of these people have been extremely valuable in much of the work that I'm going to show you today. And I have many more collaborators beyond this. And if it's not coming across, I really like collaborating. So if you have a project that you think would fit well within the skills that you are about to see that my group is good at, I'm happy to have a conversation about it. I really like interacting. When I was at Berkeley working with Ramesh, we had a very large growth group. And of course, I specialized in that at first. But eventually I became the characterizer and I did all of the beamline measurements for the whole group. And it was one of my favorite things, actually, figuring out how to tailor the experiments for the various people. It was invaluable experience. So I really enjoy having those conversations with people. I want to mention that among these collaborators, many of them are in my department. So Tudor Stanescu and Aldo, two of my theory collaborators in my department, Mohinder, Alan, and Matt. David used to be. all of these people are my department. We have a very strong condensed matter physics department. So if anyone is looking for future opportunities, I would highly recommend you give us a look. We have a lot of really great facilities within our individual labs, but we also have a pretty extensive shared facility program. So if you're looking for opportunities, we have a pretty big group, both in condensed matter physics, but we also do a large amount of optics if either of those topics interest you. So I mentioned that my group does a lot. So I'm going to mainly talk about magnetism and how we got started in that. But I did want to at least just throw out there a few teasers in case you want to check it out, that we've done a lot of other things. We've worked a lot in topological insulators. The majority of this work has been with ultra-fast optics. We have a very nice pump probe, SHG setup, second harmonic generation. We've done a lot of work. We've done some beamline experiments on this work as well. We've also worked with doped delophocytes, so I'll mainly focus on perovskite systems for what I discussed today. We've looked at frustrated magnets where you have more than one element contributing to the magnetism in the system and kind of understanding how that leads to the magnetic phenomenon that you get when you mix these different kinds of magnets. We even do some collaborations with NASA, which is a very different kind of project. We're actually looking at superconductors in these systems, and I'll kind of swing back around to this project very briefly later on after I talk about the magnetism a little bit, and then I'll kind of give a brief comparison to this work so you could see, one possible application in it and how it might be interesting. And then some of our past work was looking at combining magnetic and ferroelectric systems. So I'll talk about that here in just a second. So you see there's a wide range in our expertise in the group, and you might be wondering what pulls us together. And I would say what we really specialize is in element-specific work, ultra-fast measurements, and depth-dependent measurements. The things that I get the most collaborations in, the things that are easiest to collaborate in, tend to be the X-ray absorption measurements, where you can elementally specifically highlight or excite one of your elements and learn about the chemical nature of it. That's very fun. That's what I did as a graduate student, so I still love to do it today still. Those experiments are a lot of fun, but we're happy to talk about other things as well. So let me start with this area of multiferroics, which kind of led us into focusing on just magnetism eventually. So let me give a little bit of a teaser of this work. So maybe you've heard of a multiferroic and maybe you haven't. So let me give a definition of it. So it's a system with more than one kind of ferroic ordering in it. And the most common that people talk about, and probably the most useful, although there are some others, there are some other uses, but one of the most exciting ones is when you combine magnetic behavior with electric behavior. So let's start with magnetic behavior because that's normally the one that people are most familiar with. So let's define a ferromagnet. Of course, there are many different kinds of magnetism, and that's kind of one of the points of my talk today is we found a new kind. But the kind that people are most familiar with these days is ferromagnetism. So this is when you have a spontaneous magnetization. Even before you apply a field to the system, the spins that are nearby each other want to align in the same direction. You can have different domains in the system. But if you apply a field to the system, you can get these spins to line up. So we have a spontaneous magnetization whose direction can be changed with an applied magnetic field. Now, of course, we're most familiar with this kind of magnetism because we see it all the time. Refrigerator magnets are basically just ferromagnets. You can use them to attract things together or to repel things apart. So for fancy desk toys such as this, or if you're trying to create transportation and reduce the friction by magnetically lifting the track away from the train, you can do that. So those are the most common uses of magnets. However, there are many, many others. You can find probably 100 magnets in a given vehicle, and many more around your house. So they're often used to store information. They can be used for energy generation. So a whole bunch of different things. Magnets have lots and lots of uses, and different kinds of uses too. It's not all the same exact thing. All right, so that's a ferromagnet. I mentioned to be a multiferroic, it also has to have an electric order parameter. And this is a little less known by some people. So a ferroelectric, notice I put the definition side by side because they're very similar. So in this one, it has a spontaneous polarization. That's just separation between positive and negative charges. And the direction of this polarization can be changed with an applied electric field or a voltage. So if you have both of these order parameters in a system, which might happen if you have different ions in your system moving around in the system, that's what happens in a lot of them. You just have ions that move around. So maybe you have one ion, a cation and an anion, and they get separated or distorted in the crystal structure, and that causes this polarization that you see here. If you have both of these kinds of properties in one system, then it's known as a multiferroic. Now, just having magnetism and its electric equivalent really isn't all that interesting unless there's a neat way to link them together. So in some systems, you might be able to have both that actually interact, but it's not a given. So first of all, the kinds of things that stabilize magnetism have a tendency to destabilize ferroelectricity. So even finding these two different order parameters in the same system is relatively rare. But then even if you have them in the same system, that doesn't necessarily mean that the coupling between them is strong. And what I mean by that is what we would ideally like to be able to do is to be able to apply a voltage or a current, an electric property, and change the magnetism, the magnetic property. And that is a lot more rare, at least to have a strong coupling in a system. In fact, there aren't very many at room temperature, and the coupling is relatively small. So one of these systems is what I did my work on as a graduate student, where you have a pretty strong coupling. Bismuth ferrite is the system, in case you're wondering. But having spent a lot of time working on that system, I knew that there were some challenges with that material as well. So when it was my time to become a faculty member, I was looking for, you want to not do exactly the same thing that you did in your graduate work or your postdocs, but you want to not deviate too far either, right? You want to make a name for yourself, but demonstrate that you still have experience in the area. So I had a lot of experience with these magnetoelectric systems where you have the strong coupling between the magnetism and electricity. But I got really interested in, well, okay, we don't have a lot of systems with magnetism and ferroelectricity in the same system, but we do have a lot of magnetic systems, and we do have a lot of ferroelectric systems in industry today that they use them for piezoelectrics. For example, there are some sneakers that are built today where it can actually harness the power of you walking on your sneakers to do things like be able to charge up small electronics. Like you might be able to charge up a cell phone from just walking around on your shoes. I don't know exactly where you put your phone at the time. That might have to come later, but I'm sure somebody's thought about that. But people didn't know initially whether you would have strong coupling across these systems, across an interface between a magnetic material and a ferroelectric material. And then they also didn't know for sure how exactly it would work. So that's actually where I started. I didn't start with pure magnetism. I was looking at taking a magnetic material and coupling it with a ferroelectric material and understanding how that would happen. So let me tell you a little bit before I get into that story about how we grow the systems. So we do something called a laser molecular beam epitaxy. So that's kind of a fancy name, to be honest. It's pulse laser deposition with the addition of reflection high energy electron diffraction, which is a technique they use in MBE. But the nice thing about combining these two is it's really the best of both worlds. So MBE, molecular beam epitaxy, is a very expensive technique, both monetarily and time-wise. Pulse laser deposition, on the other hand, while it's not cheap, it's more expensive than sputtering, for example. You can do it relatively quickly, but when you add the reed system in, you can get very high quality materials. So this is kind of a schematic of how pulse laser deposition works. Basically, you take an excimer laser, you shine it on your target that has the kinds of elements that you're wanting to deposit on your substrate. You have to spend some time creating the right environment, right? So your substrate has to be the right temperature. You have to have the right oxygen pressure in the system. You don't want to hit it too fast. So the speed with which the laser hits the target, the frequency is relevant. There are actually a lot of finessing details to make it work right. But if you do everything just right, you can actually monitor as you grow with a reflection high energy electron diffraction beam. And if you monitor the diffraction pattern, mainly people just look at the main spot, but there's a whole pattern here that one can utilize. What basically happens is you get these oscillations. So I have a picture for this. So you start with a very smooth substrate, and you're coming in at a grazing angle. So your electron beam is hitting the sample, and most of it is going to reflect off towards the detector. So if you have a very smooth substrate, you're going to get a very strong signal out of it. And then as you start to grow, so you hit your laser on your target, and as atoms start to collect on the substrate, it's going to scatter some of this electron beam, right? So your intensity is going to go down. But if you are growing in such a manner that you aren't getting a bunch of clumping, but instead you are getting nice layer by layer growth. So it tries to fill in almost entirely. It doesn't have to be perfect, but it tries to fill in one layer before it goes to the next. If that happens, you once again end up with a nice smooth layer. And so you're going to get good intensity off your electron beam. And so you get these nice oscillations that you can observe and actually monitor your growth one layer at a time. It's not trivial to do, but it's doable, and it allows you to actually grow oxides with better precision than you can with molecular beam epitaxy. There may be people that would argue with me about that, but we can discuss it if anyone wants to. So it's a very nice technique for growing films. We then measure those films in a large variety of ways. Of course, we look at X-ray diffraction, we look at the magnetization, we do an amount of optics. We collaborate with people to look at the electron microscopy in an element specific manner, so we can make sure that we don't have elements diffusing across interfaces or things like this. So we have a whole bunch of different techniques. And then when we're really happy with a particular set of samples, we have a tendency to take them to a variety of synchrotron sources for doing some really fancy other kinds of experiments. So we really take a lot of techniques across our samples. We have a lot of different methods we use in our group. All right, so let me tell you a little bit about some of these synchrotron techniques, and I'm not going to be able to tell you all of it to get the picture here, but just enough to kind of be able to appreciate what's going on. So these synchrotron techniques, basically a synchrotron is just a system where they've taken electrons They're spinning them around in a circle at 99.99999% of the speed of light. So very, very fast. And of course, when you accelerate a particle around a curved path, it radiates energy. This was actually a nuisance to the people that first used synchrotrons. They were first used by particle physicists that wanted to, slam particles together at really fast speeds. And that radiation of some of their energy was problematic for them. First of all, they didn't want to get hit by X-rays, but they also wanted to keep their energy. But somebody eventually realized that, hey, maybe we can actually do something with that light. And now, today, most of synchrotron time is spent on materials characterization, not just physics, but biology and chemistry and all sorts of fields. So this is a very valuable technique for looking at the excited properties of systems. There are many, many, many ways to detect those excited properties and how these X-rays interact with the material system. And I'm not going to talk about all of them. There's a bunch. But just to kind of give you a rough idea, I'm going to talk about a simple idea of just taking your X-rays and looking at how they get absorbed into your sample of some particular thickness. You can see here I have several different elements shown up. As we change the energy of these X-rays, so that's one of the specialties of these synchrotrons, is they have a wide range of energy that their X-rays can be, which they can control by adjusting the curvature of the path that the electrons are being accelerated around. And you can see that for different elements, you see this general downward trend, but you get some edges. And these absorption edges can tell you a lot about the material. These edges have specific names. So they're actually named by, if you excite at a certain energy, you can kick out certain core levels within your system. So for example, if you kick something out of the n=2 shell, this is called the L edge. Whether you're kicking this electron all the way out of the system, or whether you're just taking this electron and exciting it to one of the empty states in your system. So this is actually more relevant. This figure on the right is more consistent with what I do in my group. I'm just exciting the system, but you can also completely kick the electrons out as well. So there are many, many different detection modes there. The cool thing about that is that you can even image your magnetic domains. So for example, here I'm looking at the manganese L edge. You'll notice that in the 2p level, of course, we have two different levels, so two different energy levels that can be excited here. They have different names, so that's what these two different peaks are. And if you look very closely, you'll notice that there's a very, very small difference in the absorption of these peaks, depending on which direction my magnetic field is applied, and that's relative to the magnetization within the sample. That looks really tiny, right? But it turns out that if you do this systematically, you can see that this really tiny difference, so here on the bottom, I'm just taking the subtraction between these two spectra on the top. You can see that here I have a whole range of sample thicknesses that this is actually a technique that you can do very quantitatively and measure the magnetization in your sample. And then if you sit at one of these places where you have a big difference in the dichroism, you can actually image your magnetic domains. And so you're going to get slightly different intensity depending on whether the magnetic domain is aligned parallel, anti-parallel, or even perpendicular to the polarization of your light. And if you want to verify that this is actually a magnetic effect and you don't just have some roughness effect, what you can do is you can either switch the polarization of the light, which is what we do a lot of, so it should reverse if this is the effect, or you can also do things with switching the magnetic field too. This is also common. All right, so this is a technique that has been used a lot to study magnetic films. And people eventually started to use it to look at coupling across systems. And that's essentially what we're trying to do in these magnetoelectrics, right? We're trying to understand a coupling between a magnet and a ferroelectric. So I'm first showing you a work of a system that's just between two magnets, but we're following kind of a similar idea. So here on the top, we have a cobalt magnetic system. So you see these cobalt domains that I had in the last slide. And then if you shine in with light that is specific to the cobalt edge, you can look at the cobalt domains. If you adjust your energy to a different element, like in this system, it's lanthanum ferrite. So if you look at the iron edge, now you can look at the magnetic domains in this anti-ferromagnet that is under the cobalt, and you'll see if you image these that they actually share the same domain structure. So these are two systems where they have magnetic domains and they are coupling across the system. So this is work very similar to some things that I did as a graduate student. So first of all, I used linear dichroism to look at bismuth ferrite domains. And then we also coupled them with ferromagnets such as cobalt and looked at the coupling across those systems, which looked very similar to what we have in this pretty example here. But when I started thinking, okay, well, I want to look at coupling between a ferroelectric and a magnet, I realized we could do exactly the same thing. And another interesting feature on top of that is you can even look at the interface between them, which this is a very unique thing. So there are a couple of unique things. First of all, you can look at a buried material, right? Something underneath the surface, but also looking at the interface. So here's an example. This is another one. So cobalt still on the surface. Now we have nickel oxide that is buried underneath, which is also an antiferromagnet. But if you use circularly polarized light on the nickel edge, you can image the interface between these two materials and actually look at the uncompensated spin at purely the interface. So we wanted to do exactly the same thing in our case of magnetoelectrics. So for our magnetic system, we were looking at lanthanum strontium manganite. And for our ferroelectric system, we were looking at lead zirconium titanite. Here we have both the manganese edge, so you can see the magnetic domains, and we also have the ferroelectric domains shown here. And we were able to look at both layers and the interface between them. Now, I'm going to admit that it wasn't quite as simple as the other example that I've shown you for the pretty example. Oh, look at how these domains are so beautifully coupled across these systems. It's not quite as beautiful, at least in this system. So on the left here, I show you the magnetic domains, which are very similar to what you saw in the cobalt example. On the right, I'm showing you the uncompensated spin at the interface. And an untrained eye would be perfectly valid in claiming I am not certain there is any correlation between these two images. And I wouldn't blame you for that at all. In fact, when I first started showing these images, it took me a very long time to convince anybody there was anything here. One of the reasons was in this field, most of the analysis that was done was very visual, right? Okay, this domain looks like that domain, so clearly there's strong coupling. But there wasn't really any form of analysis for looking at, well, what if the coupling is not quite as strong, not quite as obvious? We had to develop a few different kinds of analysis that really hadn't been developed in this field yet for verifying what exactly is going on at this interface. And I want to get beyond this topic, so I'm not going to go into great detail on those analysis techniques, but you're happy to ask me later. Feel free to ask me later if you're interested. But we actually learned a lot from this. So we were able to develop two different techniques on the left and right side of this graph, which gave us essentially similar answers that showed us a couple of important things. One, it showed us that our contrast, our intensity went down for our magnetic layer. when the magnet got thin. This is an effect I'm going to focus a lot on here soon. And in that same space, when the magnetism starts to die off, the effect that we got from the interface also died off. So when magnetic films get thin, they lose their magnetism, in fact, faster than you would even expect, just based on normalizing for the volume loss. So that's called a magnetic dead layer. It's a confusing name, to be honest. We'll explore that a bit more. But when that happens, you also lose this magneto-electric coupling. So that might not seem super surprising, but let's think about this. We're talking about coupling between a ferroelectric and a magnet. People thought this coupling would exist, but they're like, okay, if this is an interface effect, we might be best having devices that have a lot of interfaces, meaning, relatively thin films. But what this work was able to show is that there is a bit of a limit to that. So yes, it's great to have lots of interfaces, but if you make your magnetic material too thin, you will lose the effect entirely. So there is a bit of a limit on how low you can get this to go. So just a few quick, let me brag a little bit about this work. We had a lot of cool firsts. So this was the first observation of uncompensated spin at the interface between a ferromagnet and a ferroelectric. We were able, with a lot of analysis, to actually compare the orientation of those uncompensated spins, their direction, compared with the magnet. And we found that it had a preference for perpendicular coupling. First time that's been seen in a non-metallic system. It does happen in some metallic systems. And also the first observation of a potential magnetoelectric dead layer. Basically, when you lose that magnetism, you're losing the whole effect. So that's an important thing that we need to be able to control. We want that magnetism to be strong. So those are some really cool firsts. But it kind of leads us to this next question of, well, how do we control the magnetism? So this is the project that launched me into magnetism. All right, so here in this picture on the bottom, we show the magnetization versus temperature of a lot of different films of various thicknesses. And what you'll notice is between 70 unit cells to 26 unit cells, there's very little difference in the magnetization. In fact, I could show a whole range of samples from 26 to well above 70 where that magnetization doesn't change very much. So this is kind of a normalized magnetization, right? Normalized for volume. So up until 26 unit cells, our magnetization is pretty much what you would expect for the elements in the system. Maybe not perfect, but pretty close. As soon as you start going much below 26, though, you'll note that the magnetization drops off pretty dramatically. And so people have often called this having a magnetic dead layer. So basically suggesting that there's some region of the film that is magnetically dead. And if you make the film too thin, then almost all of your film is dead. Now, I think that that is not an appropriate term for it. Our evidence seems to show that it's a lot more complicated than that. Nothing is actually dead, but you do have some interesting competition going on in the system. And when you make the film thinner, it certainly leads to some more interesting dynamics in the system. So that's what we're going to talk about. Basically, we tried to understand why we have these, quote, magnetic dead layers, and we got kind of into a really interesting field. So again, I mentioned already that there are many different reasons why you might be interested in magnetism, so many different applications. So let's just launch into that. I am summarizing a lot of work, by the way, and I won't be able to hit all of it, but here's just a list of several of our recent papers talking about this exciting new effect that we found. So feel free to go check out more of it. So one of the interesting ways that we decided to launch into this, actually is a great story. So magnetic dead layers, quote unquote magnetic dead layers, is a problem that's been around for decades. If you're going to use an application where you need magnetic thin films, this is eventually going to become a problem for you. And people have been thinking about it for a long time. And yet it hasn't gone answered yet. And so that is a challenging thing to get funding for. If you want to go into a topic that has been around for decades and nobody has solved yet, right? But all of the reviewers are going to say, well, what are you going to do that's different? And if you want to get funding on something, you need to be able to say what is different. So I actually spent a lot of time thinking about this. I brought together a lot of papers in the field on magnetic dead layers, and I'm just sitting there staring at all of them like, okay, so what can I do that is different? Okay, and I notice, not surprisingly, that all of these authors are male, which is great. That's fine. And I thought, well, let me brainstorm on. I'm brainstorming. Is there any way I can use the fact that all of these authors are male and I am not, to think outside of the box a little bit? It's like, okay, well, I wasn't sure it was going to go anywhere, honestly. Like, this is probably just a waste of my time, but let's give it a try. It's a fun exercise. Like, okay, well, men do think a little bit differently than women. Diversity is great in science. There's a reason we have diversity. When men are trying to get funding from their program officers, and I'm not making fun of, I totally understand, and I have to do this too, with program officers who are mostly male. We're trying to show off whatever it is that we're being funded for. So if it's magnetism, we want it to be the biggest magnetism possible, right? Bigger is often considered better. All right, but so sometimes we're willing to play a few tricks to make our magnetization look bigger than it might be. How do you do that in the magnetic field? You apply a larger magnetic field, right? The larger field you apply in your measurement, the better aligned all of your magnetism gets, and thus you have a more impressive looking magnetization. That's great. I mean, so some people go to the mag lab in Florida or do magnetic measurements where they apply really large magnetic fields. And I have, there's some really interesting stuff that happens out there at those large magnetic fields. But like, realistically, when we're talking about devices, normally we don't want to do measurements or make a device that requires very large magnetic fields to maintain the magnetization we want, right? So it's not exactly what our magnetization is, but how we use it that's going to matter the most, right? What magnetizations that we can acquire at small fields is much more important. So this is where we got interested in, well, what happens at these smaller fields? So here I have a very typical magnetic measurement at 1,000 Ørsted. But what happens at the smaller field? So I just show the 1,000 Ørsted one here so that you can see that when we do our magnetization, whether we cool in a field or not, so that's our zero field cool versus field cool, we get very similar measurements. If we drop down our measurement field a little bit to 200 Ørsteds, a very common thing happens where the zero field cooled starts to drip down a little bit at lower temperatures. But if you go to even lower measurement fields, something really interesting happens here. Let's look at the bottom one because it's most dramatic. Here, when we measure without applying a field during cooling, so if we apply a field during cooling, we get the same looking field, almost as strong as we would get if we had done this in 1,000 Ørsteds. But if we don't cool in a field, we actually initially see that the magnetization is negative. That means opposite to the field that we are measuring in. And not only that, but look at how strong it is. Like the strength is almost as strong in magnitude, if we switch the sign, as the field-cooled measurement. And it maintains for a pretty large temperature range. And if I had measured this in 20 Ørsted, I could get it to extend even further here. So I can adjust this. So we're seeing negative magnetization at these low fields. So that's really interesting. That's some new kind of stuff. Now, this is what I basically told my student for months, that he was doing something wrong. I was convinced that it was some sort of artifact in our measuring system. So I'll show some more verifications soon. Another thing was, you know, if you're having this difference, so this deviation between zero field cooled and field cool is known to come from anisotropy in systems. So one of the logical things to think of was, well, you know, maybe we just have some preferred magnetic direction, which for whatever reason is exactly opposite to the direction that we're applying our field. And if we apply a large enough field, it counters it. So maybe that's what's going on. So we decided, well, you know, it seems weird that, because we tried a few films, that all of them would just happen to be in the direction opposite to our field that we're applying. But, you know, why don't we rotate the film? Why don't we rotate it 180 degrees? If there's some direction that it's preferring to be in, then it should still prefer to be in that direction when we rotate the film, and then it shouldn't be counter. But what would happen is we'd apply the field again, and yet again it would flip and reverse and be in the opposite direction from the field. All right, so it doesn't just have some preferred direction that it's initially at, and we just have to overcome that. No, it wants to be opposite the field if the field is small enough. That's interesting. A few more verifications before we think about that. So a lot of the concern in this field is, well, maybe this is some sort of weird artifact from your magnetization in your coils. So since we do a lot of different beamline measurements, it was pretty trivial for us to actually go and use a technique where we didn't even have to apply a magnetic field to the sample. So I told you a little bit about X-ray absorption already, and how you can get differences depending on which direction the magnetization is in the system. This one's a little more dramatic than my last example. And you could subtract these two. And you don't even need to know much about it to see that this black one, this is the subtraction. The black and red ones here on the bottom are the subtraction of the curves on the top. And we can get it to flip, to reverse, depending on whether we did zero field cooling or field cooling in the measurements. So this is a technique where we did not even have to apply a magnetic field, and we were able to get this. We also did a bunch of temperature cycling. We went through a lot of heating and cooling cycles. The main important thing here is that it's more or less following the same thing that we found from our lab-based magnetization measurements. And repeatable, that's another important thing. Just for thoroughness, we also did some neutron scattering measurements, and these are complicated measurements to be able to explain, but the thing that is obvious is between this set of curves on the top, you see the black one is on the top here and the red's on the bottom, you see they switch in this other case. So, you know, regardless of all of these weird humps and the fitting that has to go on, the fact that they switch tells you that the magnetization reverses. If you're curious about it, there's a paper link down here that you can take a look at. So here are various different measurements telling us that we have this magnetism switching. There's also some other interesting things going on that I want to point out. It's not just the negative magnetism, there's some weird stuff. So let's look at what normal hysteresis loops look like in a magnet, and then we can compare them to what they look like in our magnets that are a little bit strange. All right, so normal hysteresis loops. So I've ordered them here so you can kind of see 1, 2, 3. One is often not even shown when people are reporting data. So one is just the initial, you know, you throw your magnet in the system and people turn up the magnetic field, and they often don't even show this first loop. They often wait until they're fully saturated at a large magnetic field, and then they'll show, turning down the field and going in the opposite direction. So normally they just show the outer loop. I'm going to show one though, because it's kind of interesting here. So normally you haven't applied a film yet, a field yet. You're going to have spontaneous magnetization, but overall on the sample, it's normally not magnetized, right? It's you have a zero net magnetization until it's seen a field. And then after you apply a field, you ramp this up. Now you're in this case after the field. And of course, if you turn the field down to zero, if you have a ferromagnet, you're still going to have this alignment. It might not be as strong as when it was fully saturated. And it takes a large field in the opposite direction to get it to switch direction. All right, so that's normal. That's what normal hysteresis loops look like. Ours are similar, but a little different. So in red here, I have one, that initial starting from zero magnetic field and ramping up. And the first thing you'll notice is it doesn't start from zero, right? When we have, when we turn on the field, we immediately have a magnetization and it's negative, right? So as soon as we turn on a field, this magnetization wants to point opposite to it. So we have an initial negative magnetization as soon as we turn on a small field, right? It's not very big yet, small field. And this is shown for various different temperatures. So you can see it. You have this in each case. Another interesting thing is the first time you saturate it, this field that you need to get it to align and be fully saturated is bigger than what you need later on if you were to keep cycling this immediately one after another. If you rest it, it actually goes back to this. So this is an interesting thing because this might be very relevant to many magnetic systems. So people do these kinds of measurements on magnets all the time in industry, and they'll measure the width of these curves to understand, how much magnetism they need to set a system. And what they often find in practice is that the magnetization that they need is sometimes a little bit bigger than what you would expect based on these laboratory measurements, what these black loops look like. So perhaps we have this effect going on, maybe not necessarily exactly the same effect, but a similar effect going on in many metallic systems. So maybe this isn't just limited to our weird system that I happen to be showing you today, which is lanthanum strontium manganite, by the way, used by Intel and various industries currently today. So it's not just a weird material that's never going to be used. People are currently using it. Also, you can relate what this initial field is needed to switch. So you'll see here I have it measured at various different temperatures. This field, if you relate it to the measurement field that you're doing the measurements in the last set of curves that I showed, you can actually look at where the fraction is 1, and that will show you where this zero field cool curve switches from negative magnetization to positive magnetization. So this initial field is where this switch occurs. All right, some cool stuff. Another important note is this isn't just some initial parameter that has to be, annealed out of the sample, right? You can't just make this go away after one time. This keeps happening over and over. These 3 measurements are all on the same sample. All we had to do was wait a little bit, and this initial magnetization came back. So it's not something that, once you saturate it with a field, you don't have to worry about anymore. If, on the other hand, you saturate it with a field and you just cycle back and forth over and over again, then yes, you're fine with the black curves in the hysteresis loops. But if you let it sit, it's going to relax back to needing this larger field again. All right. Some more interesting things. So here we have loops at relatively small temperatures, 40, 120, and 200 K. All right. But what happens, so we're up to here on this curve. So 40, 120, 200 K. You'll notice in those ranges, you're having a lot of difference between the field cool and the zero field curves. But how about when we get a little bit higher, a little bit closer to where our ferromagnetism eventually goes away? Well, now some really weird stuff happens. Let's follow the loop. So I've numbered them again here for you, so it seems obvious where it's going. So let's just walk along it. So we start out at zero magnetic field. We're ramping up the magnetization. We saturate it in the direction of the field. Now I'm going to start turning down the field, turning down the field, turning down the field, turning down. Normally, I would be left with a normal ferromagnet. I'd still have magnetization. It would just maybe be a little reduced. Here, I'm turning down the field, and when the field gets small enough, it actually reverses direction. So just turning down the field, if you're at high enough temperature, so around room temperature, now we get this switch in magnetization. This is where this gets really interesting when you start thinking about applications, because now you have a magnetization that can be switched in direction with merely just adjusting very slightly the magnetic field. And we're talking about small magnetic fields. Look at the x-axis here. You know, we're in the range of tens of Ersteds. These are very small magnetic field. These aren't Tesla. These are very, very small fractions of a Tesla. And you can now switch the magnetization. So that's some exciting possible applications. All right, so what the heck is going on, right? It's so weird. So here's my analogy for what's going on. And I don't claim it to be perfect, but I claim it to be good at kind of giving you more or less an idea of what's going on. So we have some magnetic competition between two different kinds of magnetic ordering in these systems. So for the most part, a large fraction of the system is ferromagnetic, just like you would expect from the system. But we also have another magnetic phase in the system, and I'm going to claim that it's behaving like a diamagnet. I will mention, if you look at many of our papers, we've been able to model it really well, like actually super paramagnetic nanoparticles, which if I have time, I'll talk about very briefly. But let's think about it like a diamagnet. I think it's easier to think about. All right, diamagnet, you have a magnetization that wants to point opposite to the applied field. All right, and normally diamagnetism is relatively weak. So if we apply a field, if it's very large, so let's say we have these two phases, a diamagnetic phase and a ferromagnetic phase. If we apply a large field, the ferromagnetic phase just dominates, right? It goes in the direction of the applied field. That diamagnetic phase can counter it, which means we're not going to get our full magnetization. Almost similar to like having a region that is dead, right? So this is what's going on with that magnetic dead layer. We just have this other phase that is working against it. It's not really dead. It's a magnetic phase. It's just competing against it. All right, well, now let's look in the case of low fields, what happens, because this is where some really weird stuff happens. If the field that we applied is very low, the diamagnetic field still wants to counter it, and then the ferromagnetic phase has a choice to make. If the applied field is low, it might not be strong enough to align that ferromagnetic phase. So now that ferromagnetic phase has a competition between the applied field that it's feeling and the diamagnetic phase that is right next to it. So if that applied field is low enough, the ferromagnetism feels a stronger pull from the diamagnetic phase and instead decides to line up with the diamagnetic-like phase. And this results in this rapid switch. As soon as the applied magnetic field is large enough, it wins and the ferromagnetic phase follows it. So a really interesting dynamic that allows you to control this magnetism very quickly. All right, now let's think about how we might use it. Why might this be useful? Hopefully it's obvious at this point why you might try to get rid of this competition, right? You might want to maximize your magnetization. Clearly you'd want to get rid of this diamagnetic phase if you can. But maybe there's some advantages too. Maybe there are ways that we can also use this as a valuable thing. So I mentioned that I work with NASA on some superconductors. And they're actually building some next generation single photon detectors. They want to detect single photons, which is really exciting. They want to detect single photons from the heat absorption from a single photon, which is obviously really small, right? Really small. So you need some property that is extremely sensitive to temperature. All right, so superconductors are good for that, right? Because yes, they have zero resistance up to their critical temperature, but as soon as they hit their critical temperature, their resistance skyrockets really fast. So it's very sensitive to temperature. So you can kind of look at what we have going on with these systems is we also have something here that is very sensitive to temperature. So I'm not saying that this should replace superconductors for NASA, but I'm mentioning if you're going to use something that's sensitive to temperature, this is another possible way to do it. So we've been chatting with them about this too. There are probably many other ideas. So I don't know how I'm doing on time. I could talk about one other idea, but I definitely want to say that we're looking for collaborators with other ideas. My group is not an expert in devices. So if you know any experts in magnetic devices, we're very, very eager to chat with them and think about collaborations. But I want to at least briefly talk a little bit about this one other technique, if I have time. So we're interested in other applications. But one of these other applications actually tells us a little bit more about these phases, right? So I told you we have predominantly a ferromagnetic phase and something else, right? It's kind of acting like a diamagnet. So there are actually ways to look at this. So we kind of noticed this when recognizing that we could model our films in a similar way to how superparamagnetic nanoparticles have been modeled. And I want to totally thank my student Naveed for this, because I probably never would have looked into superparamagnetic nanoparticles for how to model our films, because our films look very different, right? This is an electron microscopy of our really pretty films. Looks so beautiful. There's nothing wrong with nanoparticles, but they look very different from our systems, right? It just never would have struck me that we could use the same modeling techniques to look at these. But it turns out that superparamagnetic nanoparticles do this similar thing with inverting their magnetic hysteresis loops. So that's how he got interested in that. So, they have a similar inversion in the hysteresis loops. So there's this method, a magnetocaloric method, used to actually detect these different phases in superparamagnetic nanoparticles. So in those particles, sometimes you can have competition between a ferromagnetic phase and superparamagnetism. So here's how they look at it. So basically, they look at the magnetization for a varying applied field, and they measure at different temperatures. So temperature 1 and temperature 2. And you can actually relate this to the entropy in the system. And so the area under one of these curves at a specific temperature, so the higher temperature would be this range. And then the area under this other curve is this integral here. And then you just normalize this with the difference between whatever two temperatures you're measuring at. And you do a whole bunch of measurements at various different fields and temperatures. And you can plot these lines, and you'll basically get a big peak when you have a transition in your system. So this is the transition from ferromagnetism to paramagnetism in nanoparticles. All right, so we decided to give us a try in our systems. So here are our original curves, measurements, different temperatures. And what we actually see are two peaks, which come from our two phases. So one of these is the standard transition from ferromagnetism to paramagnetism. And then we have this other phase, which I've mentioned is kind of like a diamagnet. And interestingly, it can, how much of a phase we have. So I've colored them here. So the green is like the ferromagnetic phase, and the red is like this other phase. And you'll notice that how much I have of each one depends on the field that I apply. So at these lower fields, this red region becomes more dominant in the system. Whereas at higher fields, the ferromagnetic region dominates, and that ratio between the two is pretty consistent with some of our other data. So we've been able to look at the phases, and this kind of leads us a little bit to using this technique for potential cooling. So magnetic heating and cooling is a thing. We've been able to look at the relative cooling power in our samples. And basically that just looks at the full width half max of these peaks. So we can actually find that in our systems, and I'll just kind of speed up because I know I'm getting a little low in time. And for this first film that we've tried, we note that it's a little bit smaller than in nanoparticles, but I do want to point out that the nanoparticles that we've compared it to are a little bit bigger. So one of our next goals is to look at some bigger systems. We might have an advantage here. This is a significantly thinner film, so some potential promise in using this for heating, but I'm interested to hear other ideas if people have them. So let me summarize. We've used a variety of tools, both in our lab and at national facilities, to look at a variety of materials: magnetism, magnetoelectricity, superconductivity, all sorts of stuff. I'm very happy to collaborate, so if anyone's interested, reach out to me. We've observed a really interesting magnetic effects, which results in very easy switching of magnetism aligned with the field to counter. So we get the strong negative magnetization and inversion in hysteresis loops. And it's not something we can ignore because it keeps coming back. If you let the system rest, you have to reapply this initial large magnetic field. So we can't ignore this. All right, with that, I will end and take questions.
Thank you, madam, for your wonderful presentation, an exciting tool, and thanks for sharing your invitation of collaboration research. I think many of our researchers will take this opportunity if they feel an interest in your research. So before going to end, we'll discuss about some question we have got in inbox and comment. So if you allow, we can start our discussion session.
Yes, please.
Okay, so first question I'll take from inbox. So what is Peem, photo emission electron microscopy work?
Yeah, so I mentioned in one of the techniques we used. So Peem, photo emission electron microscopy, I think was the question. This is a technique that allows you to image typically magnetic domains in your system. So I talked very specifically about how if you look at certain energy ranges, you are sensitive to the magnetic domains. And Peem is a technique that allows you to image them. You could also image other things, but magnetism is one of the most common things. You can also use it to image ferroelectric domains. I did that some in my graduate work as well. But magnetism is probably more common.
Okay, ma'am, thank you. So we have another question. So what is the ablation plume?
Ablation plume, yes. So I mentioned in our chamber. So if this is our trying to get the inner chamber, we have the laser coming down and hitting the target. And that laser ablates, kicks out a lot of the atoms out of the target, right? And it forms this plume. In fact, I had a picture. Let me share my screen again real quick.
Okay.
I have a picture.
Maybe you need to share. Yeah. Okay.
Yeah, I'm getting there. Let me try to guess. Yeah, so on the bottom here is a picture. A laser is hitting, this is the target right here. A laser is hitting right in this spot, So you rotate the target because you don't want to burn a hole in your target. So you rotate it to give it some rest, and you rotate and raster across the target, and you can see the laser is hitting this spot, and it's kicking out a whole bunch of atoms from that spot, such that it forms like this gaseous region that travels across and hits on the substrate and collects on the substrate. So that's the ablation plume right there. So I've drawn it schematically here, but this is what it actually looks like. And the color varies on, what elements are in the system.
Okay, ma'am. So thank you. Now we need to go in comment section. First question: what is the magnetic moment of a neutrino and how it is measured?
I'm sorry, I was too distracted by stopping my sharing. What was the question again?
So okay, so what is the magnetic moment of neutrino and how it is measured?
Of a neutron? Was that the question?
Yeah, neutrino maybe.
Oh, neutrino. Oh, a neutrino. So I don't know about neutrinos.
Okay.
I think the question might have been about neutrons.
Newton.
As I did mention that we were doing some neutron scattering.
Okay,
And
maybe.
that is a technique. So neutrons do have a magnetic moment, and that's why neutron scattering is sensitive to magnetism. And so it's a really nice technique for being able to look at magnetic thin films, and it allows you to do these depth-dependent measurements. So I mean, that's a really exciting area of our research that we're still getting in, because that magnetization across our film isn't exactly the same the whole way across. It has some differences. So yeah, we absolutely take advantage of the magnetization of a neutron to study our films.
Okay, madam. So thank you. We have another question. So how can we control the magnetization?
Yeah, well, I mean, there are many ways to control magnetization. You can apply a magnetic field, temperature, a lot of things. But if you're wanting to do it in an application, I might suggest looking a little bit about like MRAM. So people use magnetism in current devices these days. So, for example, Intel is very interested. So, let me give an example. Let me explain why it might be useful to use magnetism instead of the current ways we use computing. So to explain that, I need to talk a little bit about how we use current computing. So in current computing, we have zeros and ones in our computer, and that is just looking at electricity flow or not flowing between region A and region B. Right, so electricity goes from region A to region B, or it doesn't. That's your 0 or 1. So if it's flowing, that's your 1. If it's not flowing, that's your 0. We've been able to make computers much faster over time by making computers smaller. So when we make computers smaller, A and B get closer together, and thus the electron, the things can travel a lot faster between them. The disadvantage is when we've made them smaller, we've had to reduce the dimensions in all directions, not just in this direction, but also in this direction. And this has resulted in some electrons that leak in a direction not from A to B, but let's call it C. So this is just leakage. So current transistor technology, as it is already resulting in more and more electron leakage just due to the fact that we've made it smaller. So that means just having your phone or your computer on, you're having some leakage just due to the fact that we've made things very small. On top of that, if you think about it, that 1 was electricity flowing between A and B. So you're using energy just to maintain your information of the 1 there in roughly half of your bits in your computer. So that's called a volatile memory. You need energy just to maintain that information. People have been thinking a long time about non-volatile memory, where you need only to have energy if you're wanting to read the information or to change it. The current system, you need energy just to maintain it. Magnetism is a good example for how you can do that, right? Because if you magnetize a system, now that magnetism, if it's a ferromagnet, is locked there until you change the magnetic field. So you don't have to have energy there constantly to maintain that. So that might be a good way to use this in logic, for example. Even with our current systems, even though they do this magnetization in the opposite direction that you might like, that's still a magnetization. You just have to flip the direction that you want. So you could still do that.
Okay, thank you, madam. So this may be the last question. So how to estimate charge injection barrier using the photoemission electron microscopy? Peem.
Ooh. So I don't know exactly. I'd recommend chatting with a beamline scientist on this. So, for example, Andreas Scholl or Andrew Duran at Lawrence Berkeley Labs could probably at least set you up with a good person for thinking about this. However, I do know that you can look at this sort of thing. So I have looked at a long time ago, basically, how oxygen vacancies in a multiferroic could change as they move across a film. And you can actually image this with the Peem technique. So I do think that it might be possible to take a look with this system. I don't know that I'd call it easy, but it might be possible to take a look. But yeah, I would. It's been a little bit since I've done the Peem measurements, but I think they're making a lot of advances, and I would recommend chatting with the beamline scientists. They might be able to set you up in the right direction.
Okay, madam. So thank you. As we don't have any more questions, so we should conclude our discussion session. So thanks again for your wonderful presentation and exciting presentation too. And thanks for nice discussion session. So I think students and the viewers have enjoyed lots. So thanks again, and hopefully in near future, as you mentioned that you will talk some other topics, so we can arrange another webinar with you. So thanks again, madam, and hopefully we will definitely invite you after the COVID pandemic. So thanks again. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation and giving us this opportunity to announce such an important webinar. Bye for today. Have a nice day, madam.
Thank you.
Bye. Bye.